So we had been building up from position to velocity. Velocity is the rate of change of position. And then from velocity to acceleration. So how quickly is your velocity changing? That's your acceleration. And then we saw how to go back the other way. If you know about acceleration, how do you get back to velocity? You integrate, you add up all the little changes in velocity. Or to get back to your position, you add up all the little changes in position by using your velocity curve. Then we saw if acceleration is constant, that we can actually do something a little bit simpler than that. One way to think of it is, yes, you're integrating, but it's with an acceleration that's constant. What's the area under a flat line? It's a rectangle. In that case, calculus is kind of overkill. And this way is a little bit easier to work with. It's the kinematic equations. So the idea is that we have 5 of them because we have 5 kinematic variables. And so we've got one for any possible arrangement of those things. So the lines down the diagonal are, you don't have that quantity in the problem you're doing. So for instance, if you don't have acceleration in the problem you're doing, you're not given it, you're not asked for it, you probably want to use this one. And that can be a way to quickly choose which one to go with. So we had started filling out an example down here, and we're going to keep going with that. We had started filling some stuff in for this one. I want to label the picture a little bit better. So that is one thing that it seems obvious when you first start doing these kind of problems, but so few people draw pictures for them and then wonder why they're lost in the algebra and it doesn't make any sense. Well, if you're not heavily labeling your picture, you don't even know what it is you're trying to describe. So this is the speedboat going from position x0 to x. This is its displacement between those two, x minus x0, or we can write that delta x. It's doing that between a time of, we could call it t initial, but remember we had started saying, let's always assume that's 0. You start the clock at the beginning of whatever event you're studying, and then it does that between 0 and 8 seconds, and that's given in the problem. It has an initial velocity of 6 meters per second. We know it's got a positive acceleration, so it is going to speed up. It will have a larger final velocity, but we're not given that. We're just given what this acceleration is. 2 meters per second, but we could abbreviate meters per second squared. And we're asked to find the displacement. So we had already done the hard work. We had filled in what we're given and what we're asked for. And so, again, the shortcut is to look at what you're not given, in this case, final velocity. I come up here and I ask myself, which of these am I not given final velocity in? And it's this one right here. So that's the one we picked. But math-wise, it's because it has every other thing that we need. So the x initial, we're not given a specific value for that. If you're not given a value, you can always assume it's 0. Position is only defined relative to a reference point. You get to pick the reference point. It doesn't change the physics. If you decide that this boat is 3 miles from shore, and that's your reference point, and then it moves to a little bit further away than that, or if you decide where it starts is your reference point, and usually that's the easiest, you call that 0. Okay, so now we can finish this out. The velocity was 6 meters per second. Time was 8 seconds. Acceleration was 2 meters per second And then again, time was 8 seconds. We square it. We should get about, it's something like 110 to 112 meters. The one thing I'll comment on just to help make sense of this equation is what it's kind of trying to say to you. So say that the boat was not accelerating at all. It was going at a steady pace of 6 meters per second. How far would it go after 8 seconds?
48 meters?
Yes, it goes 48 meters if it's not accelerating. If it is accelerating, it's going to go more than that, and it's because it's gaining speed with each passing second. So instead of covering 6 times 8, now it's covering a little bit more because it's going a little bit faster in the next moment, and a little bit faster than that in the next moment. And that's what this second term is accounting for. That extra gain in position that you get due to the acceleration, due to the changing velocity that the speedboat has. So that's what this equation is kind of saying to you. All right, I'm gonna give you a few minutes to try this one, and then we'll do it together. So try and label everything you're given, what you're asked for, and pick a kinematic equation. You don't have to solve yet, just pick one. You're getting bored in physics class, so you decide to run into a wall as fast as you can. Reasonable. You're hoping for an impact velocity of 6 meters per second. So what variable is that telling us about? Which of these down here?
The velocity in the middle?
Yeah, so your final velocity. And this is a confusion I see pop up a lot. Just remember this is saying at time 0. So v at time 0, that's your initial velocity. This is your final velocity. Anyway, yes, it is your final velocity. We keep reading, and you can run with a maximum constant acceleration of 2.5 meters per second. Where does that go?
Acceleration.
Acceleration.
Sounds obvious, I know, but again, I've seen many things, so just gotta make sure. So starting from rest, what's that tell you?
Our initial velocity is 0.
Yeah. So it's not always given as a number. Sometimes it's text, and you have to be able to infer. So that is starting from 0. So what I was going to ask is, just from this and this, how can you tell that you're going to be speeding up? We know we are because you're going to end up smacking into the wall at a higher speed than you started, but how do we know for sure that you will be speeding up?
Acceleration is positive, and so is velocity.
Yes, or at the very least, velocity is not negative, so we're going to be taken farther away from 0 as time goes on. That acceleration is going to add on to that velocity. All right, and what are we being asked to find?
Distance.
Yeah, so we are used to, this is really displacement is what's being asked for, but as long as you're not turning around and doing loops and all these backtracking things, distance and displacement agree with each other. The case where we saw that they didn't was you go to the store and back home. You turned around. In that case, distance and displacement disagree, but as long as you're going the same direction, they're the same thing, more or less. And we are not given time. So which of these kinematic equations up here would work best?
Maybe the last one?
Yeah,
The first one.
so it would actually be the last one because we're not given time. That's the easy way to know, is look for the thing you're not given. But we could also look at it as we are given these 3 things and we're being asked for this one. So the checks are what the question involves. The dashed line is what it doesn't. And so it would be this right here. Again, I'll assume that I started at a position of 0 meters. So my initial position is 0. And that's just my shorthand for ignore it from here on because it's 0. So I have to solve for x. And to do that, I need to get it on its own. So I'll bring v0 squared over to the other side by subtracting. I'll bring 2a over to the other side by dividing. So x is v squared minus v0 squared over 2a. My final velocity is 6 meters per second. My initial velocity was 0, then 2, and positive 2.5 meters per second per second. And we get a value of 7.2 meters. Put some numbers to this that are maybe a little bit easier to think about. For meters per second to convert to miles per hour, it's about 2.2-ish. I'll just call it an easy 2 to get a ballpark number. So that's something like 12 miles per hour. It's a decent sprint. And then 7.2 meters, a meter is about 3 feet. So that's 20 to 30 feet of run-up distance. So if you're going to run at about 12 miles per hour straight into a wall, you want to give yourself about 30 feet of run-up distance, 25 to 30 feet.
Oh, I'm sorry. This so 7.2 is 25 to 30 meters.
It's 25 to
I mean,
30 feet. So 1
okay.
meter is about 3 feet. I just say that because we're used to thinking in feet in the US, so it maybe gives you a better feel for the answer. Now we're going to pivot to, instead of horizontal motion, we're going to look at vertical motion. So if you drop something, that's free fall. If you throw something straight up in the air, that's free fall, even though it's not falling at first. That's the confusing part about the name. Free fall is just you let it go and it's in the hands of gravity now. However it is that you do that. You could launch it, you could drop it, you could throw it, whatever you're doing, as long as you hand it off to gravity, that's free fall if it's in a straight line. If we get into like throwing something and it follows an arc, that'll be projectile motion, and we'll cover that in a couple chapters. So normally I would do this in class, and I don't have a recording of it, unfortunately, so I have to pose it as a thought experiment. Say I have a light book, like a little notebook, and then a very heavy textbook, and I drop them at the exact same time from the same height. Which one hits the ground first?
Heavier one?
Okay, that's a vote for the heavier one. Anyone have a different vote?
I agree.
You agree? Okay. All right, does someone want to do this experiment for me? Find something light in your house and find something heavy, stand up on a chair, drop them from the same height. Hopefully don't wake anyone up. Feel free to at some point today, because what is going to turn out to happen is they actually hit the ground at the same time. So if you don't believe me, I'm not trying to just gaslight you into believing it. Find some stuff and try it. It's the easiest experiment in the world. Stand up on a chair, drop something light and something heavy at the same time. They should both hit the ground at the same time. Now, don't use something like paper. Use a notebook or something like that for a reason I'll get to in a minute. But you're not in bad company thinking that the heavier thing hits first. In fact, that's what was thought by humans for, I guess you could say, most of human history. So Aristotle was the one who is most known for claiming that, and he said that the heavier thing will hit the ground sooner because it's got more stuff in it, and that stuff is going to be pulled towards the earth more. It's reasonable, but the thing is, no one ever actually did that experiment that I just told you about until about almost 2,000 years later, and that was Galileo, the famous Leaning Tower of Pisa. He took I think it was like a cannonball and something else. He took them up to the top of the Leaning Tower of Pisa. He dropped them both at the same time. They hit the ground at the same time. And he showed that most of human history, we were wrong about this. In other words, Aristotle set us back for almost 2,000 years by just claiming this and not testing it, and then everyone else after him being like, well, it's Aristotle. How could he be wrong? All objects actually fall with the same acceleration, meaning gain the same speed per second and hit the ground at the same time. As long as, and this is why I said don't use paper, air resistance is not too significant. If there is air resistance, that causes a problem. So we have a race we've got between a feather and a rock. We know what's going to happen in air. A few seconds later, the rock, if you drop it, it'll be down here. It's about to hit. While the feather is still just doing its thing. It's still just coasting. And for me, it always just sort of looks more like a pepper or something when I draw it. But, you know, it's just swaying back and forth and falling. So what I'm going to claim is that's only because of the air around it. If we can suck the air out of that chamber, then what we'll see instead is the rock reaches the bottom at the exact same time as the feather. And that's like a very extreme version of the experiment I just told you to try at home. This one is maybe a little bit hard to believe that the feather and rock will truly hit at the same time. But luckily, I don't have to just tell you about it. This one I can show you. So, we nowadays are blessed with the technology to test things like this. We can suck the air out of a chamber. We have vacuum chambers, and we can see which one hits first. So he's got a small vacuum chamber, and what he's going to do is he's got two magnets, one inside the chamber, one outside, and they're going to sort of clamp this feather to the top, the roof of the chamber. When he pulls the top magnet away, both the feather and the bottom magnet will drop, and the bottom magnet will act as the heavy thing, the feather will be the light thing, and you'll see that in air, they do what we expect. So this is like our baseline. Alright, feather takes its sweet time. But now he's going to pull a vacuum, so suck the air out of this chamber. And if we can take away all that air that the feather's hitting, then it also drops like a rock. And they hit at the exact same time. So again, to emphasize, in the absence of air resistance, all objects fall with the same acceleration. Anything you drop will hit at the same time. And if you are not convinced, you say, well, that's a pretty short fall. You'd probably see the difference over a much longer fall. Well, lucky for us, this was done in a giant vacuum chamber. But now with a bowling ball and a feather. And they stay side by side the entire time. And if you look at that and say, okay, but those are both in vacuum chambers, that's kind of an artificial thing. Maybe there's something about that that's affecting it. Well, they did it on the moon. I'll play audio for this. Now, of course, this is from the 60s, so it's not going to be great video or audio. But
a feather. In my right hand, a hammer. And I guess one of the reasons we got here today was because of a gentleman named Galileo a long time ago who made a rather significant discovery about falling objects in gravity fields. And we thought that where would be a better place to confirm his findings than on the moon. And so we thought we'd try it here for you. The feather happens to be appropriately a falcon feather for our falcon. And I'll drop the two of them here, and hopefully they'll hit the ground at the same time. How about that?
why did it look a little funky? And it's not because they faked the moon landing. I don't want to hear that. It would be harder to fake that, to be honest, than to just do it on the moon. What's different about the gravity on the moon, you think?
It's weaker.
It is weaker, and we'll find out a good bit later in the course why that is. The strength of gravity depends on how much mass the object has. Earth has much more mass than the moon. I'll tell you the exact numbers to see the difference between the two, but that's the idea. So, we have established that if you can take away the air, everything falls at the same rate. The next natural question is, what is that rate? How much speed do things gain each second when they're falling? And we can set up an experiment for that. I can say, all right, let's call this my initial height, y0. And I'll call the bottom of the chamber y final. All I have to do is treat this as a kinematics problem. I'll use y now since it's vertical motion. And my goal in this case is to find that acceleration, free fall acceleration. I'm going to drop the objects, so my initial velocity will be 0 meters per second. The displacement, so y minus y initial, is going to be, well, the top of this is going to be, I'm going to measure from 84.7 centimeters, and that's a specific value because I do this experiment. I have a video to show you for this one in a minute, but that's what this is over here. Of course, I'm not in a vacuum chamber. We don't have the budget for that, but as long as we assume air resistance isn't making a big change, this is okay to do. So the height of that drop is going to be 84.7 centimeters, and then it's going to fall down to 0 meters. So that's a displacement of negative 0.847 meters. It drops by that much. And I don't know how fast the two objects will be when they hit the ground, so I don't have much to work with there. But what I am going to do is I'm going to time it. I'm going to see how long it takes for the two objects to fall. So I will have this number in a second. So we'll come over here and show you that. So the setup I've got here, this stand in the middle is holding a little metal ball up at the top, and it's got this release screw. When I release it, the ball falls and that opens a circuit, and that starts this timer that you're seeing on the left-hand side of the screen. When the ball hits this pressure pad down at the bottom, it will stop the timer. And so we should get a pretty good timing of how long it takes for that ball to fall. So watch that timer on the left as I do this.
So, let's see how long it takes the ball to fall in 3, 2, 1. Okay.
All right, so 0.416 seconds is what we're working with. And it took that long to fall, 84.7 centimeters. Given this, how would I find the acceleration? Which of these kinematic equations up here is going to be most useful for that? Keep in mind we're using y instead of x now, but it's still the same variable. It's still representing the same thing.
The second to last.
Let's see. So almost, but I don't have anything about final velocity. And I am trying to find acceleration, so it shouldn't be dashed out. It should be a checked one because it's one of the things involved in the problem.
Okay. So then it would be
third
the
one.
one in the middle.
Yes, this one right here. And all I'm going to do is swap out x for y. So I am solving y minus y initial equals v0t plus 1/2 at squared. And I'm going to make a simplification because otherwise the algebra will be much worse. So v0 is 0 meters per second, so I can actually ignore this whole term. And that means I'm really solving y minus y initial equals 1/2 at squared. Or solving for a, 2 times y minus y initial over t squared. So this was a drop of 0.847 meters. And it took a time of 0.416 seconds. We square that. Can someone calculate that for me? Let me know what you get.
Negative 9.79.
Okay, yeah, let's call it an even negative 9.8 meters per second, or meters per second squared. You may have heard that number before. Now we see where it comes from. That's how much speed something in free fall gains each second, about 9.8 meters per second of speed each second that it falls. And again, we call this free fall. It is the motion of an object under the influence of gravity alone. It's drunk off gravity, under the influence of it. And this is always going to be true on Earth's surface. So you drop anything anywhere on Earth, you will measure this number. I could put an asterisk on that, but I'm not going to make things more confusing right now. So it is always downward. Anywhere on Earth you go, you drop something, it's going to fall straight down. And it will have an acceleration of negative 9.8 meters per second per second. To give a better feel for that, I'll put it in different units. So you could write it as negative 32 feet per second.
And that's gravity, right?
Yes. And so what that means right there is if you drop something 1 second later, it is going 32 feet per second. That's how fast it's moving. 1 second after that, it's going 64 feet per second. 1 second after that, 96 feet per second, and so on. Or if that's not clear, we could put it in miles per hour. So 22 miles per hour per second. You drop something 1 second later, it's moving at 22 miles per hour. 1 second after that, 44 miles per hour, then 66 miles per hour, and so on. So it only takes 4 seconds of fall for something to be moving 88 miles per hour. The size of that acceleration you often hear called g. So g is just throw out the sign, throw out the negative. And it's the one that gives you maybe a better feel for what this is saying. It's saying that the velocity changes by about 10 meters per second. I'm going to round there just to make it easier to think about. 10's an easier number to think about than 9.8. Changes by about 10 meters per second each second in free fall. That's what that means. The reason I have this highlighted, it's always downward and equal to this number right here. So this is also an always, is because you're going to mess up. At some point, I'm going to ask you a question, and the answer will be, as it always is, negative 9.8 meters per second per second. But you're going to pick a different number because it seems reasonable. And this is the confusing thing about free fall. And may not happen today, may not happen tomorrow, but there will come a day where you get asked a question that the answer is as it always is, negative 9.8, and you won't want to say it. So I'm going to warn you of that now and really stress this. This is like, put a big circle around this so you remember this one. But let's look at some of these features of free fall. So, tossing a ball straight up in the air, that is considered free fall, even though it goes up at first, because it's in the hands of gravity once you let go of the ball. So when you first throw it upward, it undergoes a displacement this way. That would be your displacement from y initial to y final, or your delta y. What is the sign of that for the upward part of the trip?
Positive.
Positive, because why?
Going up.
Yeah, it ended up higher than it started. Sounds pretty obvious. But when we come to the other side, this is the one that I, again, see lots of different answers for. So now we're looking at it starts up at the top and then falls down to the bottom. What's the sign of that displacement?
Is it still positive?
Well, did the ball end up higher or lower than it started?
Lower?
Lower, so it fell back down. What would you say about that kind of displacement?
Negative?
Negative. And that's what I had to do up here. So this isn't just like a thing to think about. This is to get the numbers right. You have to do this. If something falls downward, it's a negative displacement. What is the displacement for the entire trip? The ball goes up and falls back down.
0.
0, because it ends up at the same height it started at. This is exactly like here, you went from your house to the store. Here, you went from the store back to your house. And here, you went to the store and then came back home. It's those 3 cases we looked at a while back. Okay. Now, for part C, we're asking about velocity. So how fast the ball is moving and which way it's moving. Which way is it moving? How fast is it moving at that highest point? So up here.
Is it also 0?
Yeah, and it's because if it's at the highest point, it has to stop because it can't go any higher unless it's moving. The reason it doesn't go any higher is it stopped at that point. Or another way to think about it is imagine yourself running down a hall, like you're doing sprints or suicides, if they still call them that. You're running back and forth. In order to turn around and go the other way, you have to stop first. You got to bring your speed to 0 and then bring it back in the other direction. So this is the turnaround point, and the velocity is 0 here, because that's where the ball has got to turn around. What about the acceleration at that highest point?
Is this still 9.8?
Ooh, I almost got you though, didn't I? Was someone thinking 0? It is always negative 9.8. It's tempting to say 0 because the velocity is 0, but the acceleration, as you said, it's negative 9.8 meters per second, and that is always the case in free fall. So now we have to make sense of that, because I know it feels like it should be 0 up there if the velocity is 0. I'm going to pick a specific starting velocity. I'm going to say you throw the ball up in the air at 30 meters per second. So V0 is positive 30 meters per second. After 1 second has passed, how fast is that ball going, you think? Acceleration is telling you it's negative 9.8 meters per second, or to make this easier to think about, let's just call it an even 10. So if you started with a ball that's moving at 30 meters per second, but it experiences an acceleration of negative 10 meters per second per each second that passes, how fast is the ball going to be going 1 second from now? All right, we're going to go back up here. You started at 28 meters per second. You experience an acceleration of negative 5 meters per second. How fast are you going 1 second later?
23 meters per second?
23. And then a second after that, 18. You're taking off 5 meters per second. So let's come back to this problem with free fall. The ball is initially going 30 meters per second, or that's about 60 something miles per hour. 1 second after that, how fast is it going if it experienced an acceleration of negative 10 meters per second?
20 meters per second?
Yeah, 20. You took off 10. So now V is 20 meters per second. Acceleration is still, when the ball is at that location, negative 9.8. So 1 second after this, about how fast is the ball going?
10 meters per second?
Yeah, we're taking off 10 meters per second of speed per second. Or again, if that feels a little bit foreign, you're taking off 22 miles per hour of speed per second. And once the ball reaches this point, acceleration is still negative 9.8 meters per second. So 1 second after this, about how fast is the ball going?
0 meters per second?
Yeah, and that's how we get to 0, is that gravity saps off speed. It takes it away with each passing second. How much does it take away each second? This much, 9.8 meters per second each second. But now here's the reason we know that it also has an acceleration of negative 9.8 here. How fast will the ball be going 1 second after this? 1 second after it reaches maximum height?
Negative 10 meters per second.
Yeah, we're still subtracting 10 meters per second. But what does that mean? What's a negative velocity? It's a downward velocity. So what happens is it's going at the same speed as before, just in the opposite direction. And the only way it can ever do this, get to this right here, is because the acceleration told the ball's velocity to change from 0 to about negative 10 in the next moment. So if the acceleration were 0 up at the top, up at maximum height, the ball would just stick. It would be stuck in space and never fall back down. You need this acceleration to tell the ball what to do next. That's what acceleration is doing, is telling the velocity how to change each moment. So it told it, okay, change by 10 meters per second in the next second. And now look, acceleration is still negative 9.8 meters per second per second. So how fast will this ball be going 1 second after this? It started at
Negative
Negative
20.
20
yeah,
meters
negative
per second.
20. It started at negative 10, and acceleration said, okay, change that number by negative 10 meters per second each second. So after one additional second has passed, it's now going negative 20, meaning it is falling downward and even faster than before. So on the trip upward, a negative acceleration tells the ball to slow down because the acceleration is opposite the velocity. When acceleration and velocity are opposite, the object slows down. We learned that earlier. So that's what's happening on this side. But on the other side, acceleration and velocity are in the same direction. So the ball speeds up. It is moving downward, that's where all the negatives are from, but it is speeding up as it falls by about 10 meters per second each second. And right here, the acceleration is still negative 9.8 meters per second per second. So that 1 second after this, how fast is the ball going?
Negative 30 meters per second.
Negative 30. It's still the same acceleration as always, but now it's kind of doing a different thing. It's telling the velocity to become more negative, which means fall even faster. And that's why the acceleration can always be the same number. It can both tell something to slow down if that thing is moving upward, and tell it to speed up if it's falling downward. It can do all of that with one single number. Do we have questions on this?
Does that mean that whenever you throw something up, it'll always come down with the negative velocity that you threw it up with?
Yes, absolutely. The only caveat, the only real world thing that we're ignoring here still is air resistance, drag. And so that will make the object come back down with a slightly lower speed. It won't be exactly the same as before, but if we took away that air, it would be exactly the same. And in fact, that is why it is a very bad idea to fire a gun in the air. Because that bullet, assuming it doesn't hit too much air, is going to come back down at the same speed it went up at. Now, granted, they actually do experience quite a bit of drag, and so the bullet will slow down significantly, and we should be thankful for that, but it's still stupid to fire a gun in the air. Although, I don't know, I think in Memphis we call it a birthday party. We'll look at a similar example. A pitcher tosses a baseball up along a y-axis with an initial speed of 20 meters per second. So the baseball was thrown upward, that's a positive velocity, and this is the size of that velocity, the speed or magnitude of velocity. I want to look at this first question and see if we can solve it without any math first. You throw a ball up at 20 meters per second. How long is it going to take to reach max height, do you think?
A little over 2 seconds.
How'd you figure that out?
I divided 20 by 9.8.
Yeah, and it's because if he throws it upward at 20 meters per second, so this is V0, 1 second later, that ball is going 10. Gravity said change by 9.8 meters per second each second. 1 second after that, it's going 0 meters per second. Gravity took away another 9.8. But we know that's maximum height because the ball has to turn around at max height. That's where it has 0 velocity. So all you're really doing is saying how many seconds does it take to get from 20 meters per second to 0? It's however many times you have to subtract off 9.8. In this case, 2 times. This is 0 at max height. It's an at sign. So that's our first guess, is about 2 seconds. Now, let's do this with the kinematic equations to get a precise answer. So what can I fill in?
The initial is 20 meters per second.
Yep, in the positive direction.
Final equals 0 meters per second?
Yep. And again, we know that because this is at max height. That's where we're trying to, or where we're looking at is when the ball is at max height.
Our acceleration is negative 9.8 meters per second.
Yes, this is the other benefit. it is always this number, so you can always put it in your table for free fall. It should really be the first number you ever put in for free fall problems because you know it is negative 9.8 immediately. And what are we trying to find?
Time.
Time. So how long, that may look like a distance, but it's asking for how many seconds. So time. All right, which kinematic equation up here do you think will work best for this?
The first one?
The first one, because you could either look at it as we know we are trying to find time and we know we're given these three things, or you could look at it as I was not given anything about the displacement. I don't know what height, maximum height is at this stage. So, yeah, V equals V0 plus AT. And now you can actually see what this equation is saying. If you start with a speed of 20 meters per second, and you subtract off negative 9.8 meters per second, you can figure out the time it will take for that velocity to end up at 0. And it does come out to about 2 seconds. So this equation is really just one stating if you start with some initial velocity, acceleration is going to take off a certain amount with each second that passes. All right, and if we actually put these numbers in, it is 20 over 9.8. And we get 2.04 seconds. So a little bit more than 2, and it's because the acceleration wasn't actually 10, it was 9.8. That's the error we incur by rounding off to 10, is 0.04 seconds. Not too bad. I want you to try part B. So you're going to fill in your table, you're going to pick a kinematic equation, and this time I do actually want you to solve, to find a number for this, and we'll all compare. So what can we fill in for this table?
We know time now, so 2.04 seconds.
Yep, we can bring that down here from part A. What else?
Acceleration is negative 9.8
Yep,
meters
always
per second
is.
squared. V0 is still plus 20 meters per second.
Mm-hmm.
And we're looking for y.
Yes.
So
Well, so we also still have final velocity, right? So 0 meters per second.
0.
So in fact, we actually have quite a few options because the kinematic equations are usually like we know 3 things, want to find a 4th. Here we know 4 things, want to find a 5th. So we can use any kinematic equation where we have 3, pick any 3 of these, and need to find this. So we actually may have had quite a few different approaches to this one. So you said, which one?
The first one?
Okay, so for the first one, is it going to help us find a height? So an x, or in this case, a y value. Does x or y show up in the equation?
Oh, no.
No, so it's not wrong to use this one. It's just not going to give us the information we're looking for. Do we have another guess?
I used the last one.
Okay, the last one. So let's see. And again, I'm just replacing x with y because it's vertical motion. So this one looks good to me. We can use it to solve for y. I'm going to say y initial was 0 meters because I'm going to use his hand as my reference point. This is y initial is 0. And so I really just need to solve this. And I do get that y is v squared minus v0 squared over 2a. V final was 0 meters per second. V initial was plus 20. And then acceleration was negative 9.8. And what did you get for that?
20.4 meters.
Sounds good to me. So 20.4 meters positive because it is above where the ball started. But again, that's a nitpick. One thing to mention here that is not so much a nitpick is that if I had not used a negative here, like I'm supposed to for my acceleration, I would have gotten a negative answer right here, right? Because this negative cancels out this negative. If I didn't do that, I'd be saying that the ball goes underground. So I would know something's wrong. Similarly up here, if I hadn't have used negative 9.8, I would have gotten that it takes negative time for the ball to reach maximum height. Again, a little concerning. So it's important to keep track of signs not just for physics, but for your own sanity. Because if you do a problem and you find out it takes negative time to do something, I think you'll be a little concerned. So keep track of your signs with this stuff. Did anyone use a different kinematic equation? All right, well, you could have. You could have used this one. Because we know time, we know the initial velocity, we know acceleration, and we can use it to find that displacement. You could also have used this one. But no matter which one you use, you should get that same answer. They should be consistent with each other.
Did you use any of the 4 equations besides the first one, or are there only 3?
Absolutely, yes, you could. So you have a lot of options for this one. And that's typically the case once you've already found some information using a different kinematic equation. Which of those do you think is best, though? They all give the same answer, so none of them are wrong, but there is one that's maybe the best one. What's different about this one versus the other 3?
It's time free.
Yes, it does not depend on time, which is something we found. Never trust yourself if you can get away with it, because we are human, we are prone to error. So it's better to use the information you're given than to use what you've inferred previously. Now, I don't think that's good advice in general in life. I mean, do trust yourself, trust your instincts. This is just, it makes sure that if you make an error earlier on, it doesn't propagate. It doesn't keep going with you with each successive problem. We got one last one, and now the situation has changed. So we have to be careful. We have to reevaluate what it is we know and want to find. So it asks, how long does the ball take to reach a point 5 meters above its release point? So I'll say this is about 5 meters above the release point, so in the positive direction. The question is, how much time does it take? How long does it take for it to reach that height? So what can I fill into my table?
Yeah, but the displacement is 5 meters, or
Yep.
positive 5 meters.
Yep. Okay, what else?
Initial velocity is 20 meters per second.
In the positive direction. What can we always fill into these for free fall?
The acceleration, which is negative 9.8 meters per second
Yep.
I don't think so, because since it's not at its maximum, we don't have a final velocity already
Great.
given.
Yes. Yeah, so that final velocity we don't know anymore. It's not something we can put in our table, and that is something that can be messed up if you're not thinking about the situation you're analyzing. I no longer am looking at when the ball's up here, so I don't know anything about its velocity at that point. All right, which kinematic equation is going to help us with this? It's the one where we don't know final velocity, right? So this one right here.
Middle one?
That one shows up quite a lot, you've probably noticed. It's pretty useful. So y minus y initial equals v0t plus 1/2 at squared. Here's the sad part, though. I'm going to put in some numbers, and you'll see what happens. So this was 5 meters. Again, we can say the initial height was 0 and measure from there. V initial is 20 meters per second. Acceleration is 1/2 times negative 9.8, and then t squared. I'm now going to throw out units, so it's a little bit easier to read this. So 5 equals 20t. 1/2 times negative 9.8 is negative 4.9. I've got to solve that for time, for t. How do I do that?
Subtract 5 from both sides and then solve it as a quadratic equation?
Unfortunately, yes. And I'm gonna, just so I have a positive number out front, it's just a thing in my brain that likes to happen. I'm gonna move everything over to this side, so it'll be 4.9 t squared minus 20t plus 5 equals 0. As you said, it's a quadratic equation, so we've got our coefficients a, b, and c. Quadratic formula says that's negative b plus or minus square root of b squared minus 4ac all over 2a. And so I'll just put in my values. B is negative 20. Remember, it's everything out front of that linear term. So negative 20, negative of negative 20 plus or minus square root. Again, b is negative 20. We square it. Minus 4. A is 4.9. C is 5. And then all over 2a, so 2 times 4.9. And so we have two roots, the plus and the minus. If we calculate, we'll get either 0.27 seconds or 3.8 seconds. Why do I have two answers? Physically, why? I just said math-wise, it's because I have a plus and a minus right here. But why physically should I have two answers?
Once when it's going up and once when it's coming back down.
Exactly, it's at 5 meters twice. Once on the way up and once on the way back down. And it's telling us both. That's kind of neat that it's telling us both for when it's rising and for when it's falling. The math automatically spits that out. And if you've been asking yourself for years, what's the point of the quadratic formula? When will I ever need this? That's very fair. But I will at least say that every time something falls, every time you throw something, secretly there's a quadratic hiding in there, and secretly there's a parabola hiding in there. So that other thing that you always wonder, what's the point? It's life. It happens in real life. Now, will that help you do your taxes? Absolutely not. But it's something that does happen. So any questions on this? I'm just going to highlight my answers here. That does also mean we're backloaded on quizzes, so we have 2 and Chapter 1. We're still going to do Chapter 1, and then we'll probably have to do Chapter 2, the class right after. But anyway, we'll just say for Thursday that it's going to be the Chapter 1 quiz, just to get that out of the way. All right. In Chapter 3, we can finally exit the 1D world we've been living in for the last couple chapters. You can now move to the left and right and up and down. It's crazy. But that leads to or brings with it some problems. The main problem is, in the last chapter, we got away with using just a plus or minus, but that's because there were only 2 possible directions. What do you do when you add 2 more directions to that? Or even 2 more on top of that, because you could have 3D motion. And that's what we have to figure out in this chapter. So we're going to use vectors. We're going to kind of bulk them up, give them a little bit more of an identity than just it's something that has a direction to it in this chapter. And that'll give us some tools to analyze 2D and 3D motion. So the easiest vector to think about is displacement. You started here, you went there. So maybe between 2 towns, P to Q. Your displacement is just the direct path, pointing from your initial position to your final position. So start here, end here. That doesn't mean that that's actually what you did. Displacement is the most direct path. It is the shortest possible distance you could go, the as the crow flies distance. But you could have actually taken a very roundabout route to get from here to here. This could have been your actual path. You could have also done something like that. That could have been your path. But in all cases, the displacement is that red vector. It's just saying, I started here, I went there. It doesn't care about the details of how you got there. So it says nothing about the actual path taken. So say I take a trip from P to Q. I'll call that my first displacement. And it's 10 miles to the east. And then I take a trip from Q to R. So 5.5 miles at 55 degrees north of west is going to be this angle right here. The question is, how far is city R from P? So this is 10 miles. This is 5.5 miles. Any ideas for this? And then the squiggly line is, again, the possible path you could have taken. It can be something very different from these displacements, these direct paths. Well, if you don't have any clue, good. That's kind of the point. We've reached a problem where even though it's very clear what it's asking, how far away are these two cities, I don't know how to answer that. We knew just fine if it was 1D. So for instance, if it was along a line of 10 miles and 5.5 miles, I know how far apart these two cities are. How far apart are they?
15.5.
Yeah, that works great in 1D. And even if I had to backtrack, I went 10 miles. And then I was like, oh, I missed city R. It was actually back the other way. So I backtracked by 5.5. I know how to deal with that. How far away is city P from city R?
4.5.
4.5. I just subtract. So in 1D, it's absolutely no problem at all. 2D opens up this whole new world of possibilities of intermediate values between those two extremes, and I don't know which one it is. I'll tell you now, it's 8.2 miles. But we have to figure out in this chapter how in the world I figured that out. That's where I'll stop. Any questions? All right, well, if not, I will see y'all in person on Thursday, and we will have our Chapter 1 quiz. I also need to get up the Chapter 2 homework, and then Chapter 3 graded practice. I'll space the dates out on those a little bit, and whatever else is due is due. It's in the hands of Canvas once I post it, because I'm bad at remembering those dates. Any other questions?
Will we have to memorize the kinematic equations?
No, I'm not a fan of memorization. I don't think it's useful because you will always be able to look these things up in real life if you need to. So what I will say is for things like exams, I give you the list of equations. I give you a list of all the equations I think you might need to do the exam. I don't necessarily give you this because it takes up a lot of space, but I do allow you a cheat sheet on exams, and you can put whatever you want on there, and this is probably one of those things you would want to put. For quizzes, it doesn't matter anyway because I don't ask you to calculate anything on quizzes, so you wouldn't need these. So the short answer is no, you don't need to memorize them. Any other questions? Have a good day, y'all. I'll see you on Thursday.